What if everything we think we know about the expanding universe is missing a crucial piece of the puzzle? For nearly a century, redshift data, the stretching of light from distant galaxies, has been the cornerstone of cosmology, the smoking gun that convinced us the universe is growing ever larger. Edwin Hubble's groundbreaking observations in the 1920s seemed to settle the debate, painting a picture of cosmic expansion that's been taught in textbooks ever since. But what if the data hiding in plain sight tells a more complicated story? Recent discoveries have uncovered 28 overlooked clues buried in that same redshift data, anomalies that don't quite fit the neat narrative of an evenly expanding cosmos. These aren't just minor glitches, they're potential cracks in the foundation of modern astrophysics, hints that our understanding of the universe might be due for a radical rewrite. Picture this: you're staring at a map of the cosmos, tracing the paths of galaxies as they retreat from us, their light shifted toward the red end of the spectrum. It's a beautiful, elegant story, one that suggests a universe born from a single explosive moment and stretching outward in all directions. But look closer, and the map starts to show strange inconsistencies. Some galaxies are moving faster than they should. Others seem to cluster in ways that defy predictions. Even the rate of expansion itself doesn't line up perfectly depending on where or how you measure it. These aren't just random blips, they're systematic deviations, patterns that suggest something fundamental might be missing from our equations. Could it be that redshift, the very tool we've relied on to measure the universe's growth, is hiding secrets that challenge the bedrock of cosmology itself? That's the journey we're embarking on today. We'll dive deep into those 28 overlooked clues, each one a thread in a larger tapestry of cosmic mystery. From puzzling galactic rotations to unexpected voids in the fabric of space, these anomalies force us to ask uncomfortable questions. Is dark energy, the mysterious force driving accelerated expansion, really what we think it is? Could there be unknown physics at play, or even flaws in how we interpret the data? This isn't just about tweaking a theory. It's about confronting the possibility that our universe is far stranger and more complex than we've dared to imagine. So buckle up, because by the time we're done, you might never look at the night sky the same way again. The first clue shaking the foundations of cosmic expansion comes from something that should be impossible: galaxies moving together in tight clusters, bound by gravity, yet displaying redshifts that vary wildly from one another. If the universe were expanding uniformly, galaxies within the same cluster should share nearly identical redshift values, all drifting away from us at similar speeds. But the data tells a different story. Take the famous Stephan's quintet, a cluster of 5 galaxies where one member shows a redshift vastly different from its neighbors. According to conventional models, this outlier should be millions of light years behind the others, yet there it sits, clearly interacting with them as if it's part of the group. How can galaxies so deeply entwined have such mismatched redshifts? This isn't an isolated case. Astronomer Holton Arp spent decades cataloging hundreds of these anomalies, arguing that redshift might not always be a reliable indicator of distance. He proposed that some redshifts could be intrinsic, woven into the fabric of certain galaxies due to unknown physical processes rather than cosmic expansion. Picture a car's horn blaring at different pitches, not because the car is moving, but because the horn itself is somehow altering the sound. Arp's controversial work suggested that quasars, those brilliant cosmic beacons, often appear unnervingly close to galaxies with mismatched redshifts, as if they were ejected from them. Yet instead of sparking a revolution, his findings were largely sidelined. dismissed as statistical noise or measurement errors. The resistance to these anomalies raises a provocative question. Why does mainstream cosmology cling so tightly to the idea that redshift solely measures expansion? Part of the answer lies in the sheer elegance of the Big Bang model. It's a framework that explains so much, from the cosmic microwave background to the abundance of light elements. But science progresses by confronting inconsistencies, not ignoring them. When galaxies in the same cluster defy gravitational expectations, when quasars align with galaxies in ways that challenge distance measurements, it's not just a puzzle, it's an invitation to rethink the rules. Could there be another layer to redshift, a hidden variable we've yet to uncover? Or does the universe have a way of tweaking the laws of physics in places we least expect? Now, let's turn to the second clue, one that might make you question whether the universe operates like a finely tuned instrument rather than a smoothly expanding canvas. It's called quantized redshifts, and the idea is as startling as it sounds. Instead of galaxies displaying a continuous range of redshift values, they seem to cluster around specific, evenly spaced intervals, almost like rungs on a cosmic ladder. This isn't some fringe speculation. It was first documented by astronomer William Tift in the 1970s, who noticed that the redshifts of galaxies within groups weren't randomly distributed. They appeared to jump in distinct steps, as if something was dictating their motion in precise increments. Think of it like a piano where only certain keys produce sound, leaving gaps where notes should exist. If redshift were purely a measure of cosmic expansion, as the Doppler effect suggests, we'd expect to see a smooth, unbroken spectrum of values as galaxies drift farther away at varying speeds. But Tift's data, and later studies by researchers like Bruce Guthrie and others, revealed something far stranger. The redshifts of galaxies, particularly in tightly bound systems, seem to prefer specific multiples of a fundamental value, roughly 72 kilometers per second. It's as if the universe has a hidden rhythm, a set of rules we haven't yet decoded. This discovery throws a wrench into conventional cosmology. If redshift is truly quantized, it implies there's more at play than simple expansion. One possibility is that gravity itself operates differently on cosmic scales, creating preferred energy states for galaxies. Another, more radical idea is that redshift isn't solely about motion. It could reflect something intrinsic to the structure of space-time, like vibrations in the fabric of the universe. Imagine the cosmos as a giant bell, ringing at specific frequencies with galaxies humming along to its tune. The implications are profound. If quantization is real, it challenges the very foundation of how we measure distances and interpret the universe's expansion. Could there be a deeper layer of physics, one that ties redshift to quantum processes or even the underlying geometry of reality? Or does this phenomenon hint at a universe that's more structured, more orchestrated than we ever imagined? Mainstream astronomy has often dismissed these findings as artifacts of small sample sizes or measurement errors, but the persistence of the pattern across independent studies keeps the debate alive. So here's the burning question. If the universe really is tuned to specific frequencies, what's the instrument playing the melody? And more importantly, what happens if we learn to listen? Now let's examine the third clue, one that might make you question whether we've been misreading the cosmic map entirely. Across the universe, astronomers have spotted high redshift objects like quasars appearing suspiciously close to low redshift galaxies, often connected by faint tendrils of gas and dust. These aren't just random overlaps, they look like genuine bridges of matter, as if these distant, energetic objects are physically tethered to galaxies that, according to their redshifts, should be far closer to us. If redshift were purely a measure of distance, this would be impossible. Imagine seeing a kite flying a mile away, only to realize its string is tied to your neighbor's fence. That's the level of cosmic contradiction we're dealing with here. Take the case of NGC 4318, a seemingly ordinary spiral galaxy. Hubble images reveal not one, but multiple quasars positioned eerily close to it, some even aligned along its polar axis. These quasars have redshifts indicating they're billions of light years away, yet their precise alignment with the galaxy's structure suggests an intimate connection. Even more baffling filaments of ionized gas appear to stretch between the galaxy and the quasars, like cosmic umbilical cords. According to standard cosmology, these quasars should be so far away that any visible link to NGC 4318 would be impossible. Yet the evidence is right there in the data, whispering that something doesn't add up. This phenomenon isn't rare. Astronomers have catalogued dozens of these peculiar pairings, where high redshift objects cling to low redshift galaxies like shadows. One leading explanation, championed by researchers like Jeffrey Burbidge, is that quasars might not always be the distant behemoths we assume. Instead, they could be ejected from active galaxies, born with intrinsic redshifts that don't reflect cosmic expansion. Picture a fountain spraying droplets. Each droplet might inherit properties from the source, not because it's far away, but because of how it was launched. If true, this would mean some quasars are local eruptions, their extreme redshift signaling not distance, but an entirely different astrophysical process. The implications ripple through cosmology. If even a fraction of high redshift objects are physically linked to nearby galaxies, it undermines the assumption that redshift is a universal yardstick for expansion. Could what we've interpreted as an accelerating universe be, in part, a misinterpretation of these anomalies? Skeptics argue that these alignments are chance projections, mere tricks of perspective. But the statistical unlikelihood of so many precise connections, paired with visible matter bridges, makes that defense feel increasingly shaky. Science thrives on discomfort, and these cosmic contradictions are the kind of discomfort that might just lead to the next breakthrough. So the question isn't just whether we're misreading redshift, it's whether we're ready to admit how much we still don't understand. The fourth clue in our cosmic detective story takes us to a test that was supposed to settle the debate once and for all, the Tolman surface brightness test. Named after physicist Richard Tolman, this elegant method was designed to confirm whether the universe is truly expanding by measuring how the brightness of galaxies should fade over vast distances. According to expansion theory, as light stretches across an expanding cosmos, galaxies ought to appear not just redder but dimmer in a very specific way. Their surface brightness, or how much light they emit per unit area, should drop predictably with redshift. But here's where things get messy. When astronomers actually apply this test, some galaxies stubbornly refuse to follow the script. Instead of fading as expected, they shine brighter than expansion models allow, as if the universe forgot to dim the lights. Take the case of ultra-diffuse galaxies, those ghostly, sprawling structures with stars spread so thin they should be nearly invisible across cosmic distances. Yet when researchers like astronomer Eric Lerner analyzed their surface brightness, they found these faint giants defied Tolman's predictions. Some appeared up to 10 times brighter than expansion models could explain. It's like holding a flashlight at arm's length, then moving it farther away only to find it somehow stays just as bright. This isn't a trivial discrepancy. It's a direct challenge to the idea that redshift always equals expansion. If the light from these galaxies isn't dimming as it should, perhaps redshift isn't purely about stretching space. Maybe something else, something we haven't accounted for, is bending the rules. The mainstream response has been to attribute these anomalies to observational pitfalls. Dust clouds might magnify light, or galaxy evolution could skew measurements. But critics point out that these explanations often feel like patches on a fraying theory. If Tolman's test fails even occasionally, it raises a deeper question. Are we misinterpreting the universe's glow? Some researchers propose alternatives like tired light models, where photons lose energy over time without cosmic expansion. Others suggest intrinsic redshift mechanisms, where galaxies themselves alter light in ways we don't yet understand. The debate isn't just academic, it cuts to the heart of how we measure the cosmos. When a foundational test like Tolman's wavers, it doesn't just hint at missing pieces. It suggests we might be holding the map upside down. So where does this leave us with a universe that refuses to be boxed into tidy equations? Every anomaly, every galaxy that shines too bright, every redshift that defies expectation is a whisper from the cosmos urging us to look deeper. The Tolman test was meant to be a seal of approval for expansion. Instead, it's become a mirror reflecting back our own uncertainties. And in that reflection, there's an exhilarating possibility that the real story of the universe is still being written, and we're just beginning to read the pages. The fifth clue takes us to one of cosmology's most trusted measuring sticks, type Ia supernova. These stellar explosions are often called the universe's standard candles because they burn with such consistent brightness that astronomers can calculate their distances with remarkable precision. Or at least that's the theory. When we compare their redshifts, how much their light stretches as the universe expands, to their actual luminosity, something unsettling emerges. A fraction of these supernovae don't just deviate slightly from expectations, they outright defy them, shining brighter or dimmer than their redshift should allow. It's like watching a row of identical light bulbs, each wired to the same power source, only to find some flickering unpredictably, as if hidden hands are tampering with the circuit. This inconsistency isn't just a minor hiccup, it feeds directly into the biggest headache in modern cosmology, the Hubble tension. For years, scientists have wrestled with conflicting measurements of the universe's expansion rate. Some methods, like tracking the cosmic microwave background, suggest one speed. Others, like supernova observations, suggest another. The gap between them is too wide to dismiss as error, and now these anomalous supernovae are adding fuel to the fire. If standard candles aren't as reliable as we thought, could part of the tension stem from misreading redshift data? Take the case of supernova 2322, which appeared in a galaxy with a redshift implying it should be faint, yet it blazed far brighter than models predicted. Or its counterpart, supernova 1987A, whose light curve didn't match its redshift's expected behavior. These outliers aren't noise, they're signals, hinting that something fundamental might be missing from our cosmic playbook. The usual fix for such puzzles is dark energy, the enigmatic force invoked to explain why the universe's expansion is accelerating. But what if dark energy is less of an explanation and more of a placeholder? Some researchers, like physicist Sabir Sarkar, argue that these supernova anomalies suggest a more radical possibility, that redshift isn't always a clean proxy for expansion. Could intrinsic properties of supernova, or even the space they inhabit, alter their light in ways we haven't accounted for? Imagine blowing up a balloon with patches of uneven elasticity. Some areas stretch smoothly, others resist. If the fabric of space-time has similar hidden variations, supernova might not be the uniform beacons we assume. The stakes here are enormous. If even a subset of supernova have redshifts skewed by unknown physics, it could mean our map of the universe is subtly distorted, like a mirror with invisible warps. And that distortion might be masquerading as dark energy, a cosmic mirage born from misinterpreted data. critics counter that these anomalies are rare, that most supernovae still fit the mold. But in science, outliers are often the cracks where breakthroughs seep in. When the universe hands us standard candles that flicker unpredictably, it's not just asking us to adjust our measurements, it's daring us to rethink our assumptions. So the next time you hear about dark energy's mysterious grip on the cosmos, remember, the mystery might not lie in the void between galaxies, but in the light we thought we understood. Now we come to the sixth clue, one that might make you wonder if the shape of a galaxy holds the key to unraveling redshift secrets. Studies have uncovered a peculiar pattern. Spiral galaxies, those majestic pinwheels of stars, often display systematically different redshift distributions compared to their elliptical cousins, the smooth, football-shaped giants. If redshift were purely a measure of cosmic expansion, this shouldn't happen. Like cars on a highway, all galaxies should follow the same traffic rules, their redshifts reflecting uniform motion. But the data tells a different story, one where morphology, the very structure of a galaxy, seems to whisper into the redshift equation. Take the work of astronomer Vera Rubin, who noticed that certain spiral galaxies showed redshift anomalies in their outer arms, where stars rotated faster than expected. This wasn't just about dark matter's gravitational pull. It hinted that something about the spiral structure itself might influence how light stretches. Later studies, like those by astronomer Jack Sulentic, found that spirals in galaxy clusters often had redshifts slightly offset from ellipticals in the same regions, as if the universe had handed them different rulebooks. One striking example is the Sombrero Galaxy, a hybrid with both spiral and elliptical traits. Its redshift profile doesn't neatly fit either category, blurring the line between shape and spectral behavior. Mainstream cosmology often dismisses these discrepancies as side effects of galaxy formation or measurement noise, but critics argue that the consistency of the pattern suggests something deeper, that intrinsic properties like magnetic fields or plasma dynamics in spiral arms could be imprinting extra redshift onto light. Picture two singers hitting the same note, but one's voice carries an unseen echo. If spirals are adding their own echo to redshift, it would mean we've been conflating cosmic expansion with local astrophysics, like mistaking a ripple in a pond for the tide. The implications ripple far beyond classification. If galaxy morphology tweaks redshift, it could mean our cosmic distance ladder has hidden rungs, steps we didn't know were there. Some researchers, like astronomer Ricardo Scarpa, propose that active galactic nuclei or star-forming regions in spirals might generate additional redshift through mechanisms we don't yet understand. Others caution that selection biases, like how we tend to study brighter, nearer spirals, could skew the data, but when the same patterns persist across independent surveys, the case for a deeper link grows harder to ignore. So why has this clue been sidelined? Part of it is practicality. Redshift is already a messy metric, and adding morphology into the mix would complicate an already fragile measurement system. But science thrives on complications. They're often the cracks where truth slips through. If the shape of a galaxy can bend light's fingerprint, then every spiral in the sky isn't just a cosmic whirlpool. It's a question waiting to be asked. The seventh clue might be the most baffling of all quasars that refuse to play by time's rules. In an expanding universe, light from distant objects shouldn't just stretch in wavelength, it should also slow down in time. Imagine a cosmic tape recorder. As space expands, the music playing on it, the flickering light of a quasar should sound deeper and slower. This phenomenon, called time dilation, is clearly visible in supernova. The farther away they are, the more their light curves stretch out, like a film projected in slow motion. But when astronomers turn their telescopes to quasars, those brilliant beacons with redshifts suggesting they're billions of light years away, something strange happened. Their flickering patterns didn't slow down at all. Take the landmark study by Mike Hawkins, who analyzed the light curves of over 900 quasars. If the universe were truly expanding as predicted, their variability, the way their brightness dances over months or years, should appear drastically slowed to our eyes. Instead, the flicker rates matched those of nearby quasars, as if the fabric of space-time had forgotten to stretch their clocks. It's like watching two metronomes, one placed at the far end of a room, yet both ticking at the same relentless pace. This isn't just a minor inconsistency, it's a direct violation of a cornerstone of relativistic cosmology. Time dilation isn't optional, it's baked into the math of expansion. So why do quasars act like they're exempt? One possibility is that quasar light doesn't always obey the textbook rules of redshift. If some of their apparent distance is intrinsic, caused by local physics rather than cosmic expansion, their light might not carry the expected time-stretching signature. Picture a strobe light in a foggy room. The fog might redden and dim the light, but the strobe's blink rate stays stubbornly constant. Some theorists, like physicist Jayant Narlikar, argue that quasars could be younger, more local objects ejected from active galaxies, their high redshifts reflecting violent birth processes rather than vast distances. Others propose that the extreme environments around supermassive black holes where quasars are born might warp light in ways that mimic cosmic expansion without the accompanying time dilation. Then there's the supernova comparison, which sharpens the mystery. When we observe Type Ia supernova, their light curves stretch beautifully with redshift, just as relativity predicts. But quasars, with redshifts often 10 times higher, show no such effect. It's as if the universe has two sets of rules, one for dying stars, another for its most luminous monsters. Skeptics suggest quasars might have such complex variability that dilation effects get washed out in the noise. But Hawkins's work controlled for these factors, and the absence of dilation held firm. This leaves cosmology at a crossroads. If quasars truly lack time dilation, it undermines the assumption that their redshifts uniformly measure cosmic expansion. Maybe the universe's expansion isn't as smooth as we thought, or maybe redshift is a mosaic of different phenomena, some cosmological, some local. The quasar enigma doesn't just challenge our models, it forces us to confront how much we still don't know about light, time, and the fabric of reality itself. And when the brightest objects in the cosmos defy the laws we thought were universal, it's not just a puzzle, it's an invitation to rewrite the rules. The eighth clue takes us into the realm of cosmic rhythms patterns so precise they seem almost mathematical. Across massive galaxy surveys, astronomers have stumbled upon a phenomenon that defies randomness, redshifts repeating at eerily specific intervals, like notes in a grand celestial symphony. These aren't just isolated quirks, they're statistical echoes that appear again and again, as if the universe has a hidden metronome ticking beneath the chaos. The Sloan Digital Sky Survey, for instance, revealed galaxies clustering at redshift intervals of roughly 0.001, a faint but unmistakable beat in the data. Multiply that by the vastness of space, and the odds of this happening by chance vanish into the realm of impossibility. What makes these periodicities so unsettling is their scale. Unlike the quantized redshifts we discussed earlier, which often appear within tight galactic groups, these patterns emerge across colossal volumes of space, spanning billions of light years. Imagine throwing a handful of sand onto a drumhead and watching the grains arrange themselves into perfect concentric circles. That's the level of order we're talking about. Some researchers, like astronomer William Napier, argue these periodicities could trace back to a cosmic lattice, an underlying structure to space-time itself, like the atomic scaffolding of a crystal. If true, it would mean the universe isn't just expanding, it's vibrating, resonating at frequencies we're only beginning to detect. The mainstream response has been cautious, attributing these patterns to large-scale clustering or survey artifacts. But the data resists simple explanations. When you find the same redshift intervals repeating across independent surveys, from the 2-degree field Galaxy redshift survey to the more recent DAISY data, it's hard to dismiss as noise. Even more provocative are models like the Carlson periodicity, which predicts redshift peaks at precise values 0.061, 0.096, and beyond with uncanny accuracy. It's as if the universe left a signature, a breadcrumb trail of numbers waiting to be decoded. Could these periodicities hint at something beyond standard physics? Some theorists speculate they might reflect boundary conditions in a finite universe like echoes bouncing off the edges of reality. Others propose they're artifacts of dark matter's unseen architecture, or even relics from the universe's birth, frozen into the fabric of space. Then there's the radical idea that light itself might behave differently over cosmic distances, its redshift influenced by interactions with an undiscovered field or dimension. Whatever the answer, these patterns aren't just curiosities. They're fractures in the smooth facade of cosmic expansion, places where the universe whispers that its rules might be more intricate and more beautiful than we ever imagined. So here's the challenge these periodicities pose. If redshifts can carry hidden rhythms, what else have we missed in the noise? And if the cosmos truly has a pulse, how do we learn to listen? The ninth clue takes us from the vastness of the cosmos to our own cosmic backyard, where 2 tiny human-made objects, the Pioneer probes, began drifting off course in ways no one could explain. Launched in the 1970s, these spacecraft sailed through the solar system with near-perfect precision until they didn't. By the 1980s, tracking data revealed an anomaly. Both probes were slowing down slightly more than expected, as if an invisible hand were tugging them backward toward the sun. This unexpected deceleration, dubbed the Pioneer Anomaly, baffled scientists for decades. But here's where it gets eerie. The same gravitational mysteries that haunted Pioneer might hold the key to understanding Redshift's inconsistencies. At first glance, the connection seems tenuous. One involves spacecraft, the other, the stretching of light across billions of light years. But dig deeper and parallels emerge. Just as the Pioneer probes experienced an unaccounted-for drag, some galaxies exhibit redshifts that don't align with their predicted motion. Could both phenomena stem from the same underlying physics? One provocative theory, modified inertia, suggests that inertia itself, the resistance of objects to changes in motion, might behave differently at extremely low accelerations, like those experienced by Pioneer in the quiet depths of space. If inertia isn't constant, it could subtly alter how gravity interacts with matter, tweaking the motion of spacecraft and the trajectory of light alike. Then there's the shadow of hidden mass. To explain Pioneer's anomaly, some researchers proposed unseen clouds of dust or dark matter lingering in the solar system. Similarly, redshift discrepancies often lead astronomers to invoke dark matter's gravitational influence. But what if the hidden mass isn't particulate? What if it's something more exotic, like a field or energy gradient permeating space? Picture wading through a river. The water's current tugs at your legs, unseen but undeniable. If space itself harbors such gradients, they might nudge spacecraft off course while also imprinting extra redshift on distant starlight. The most tantalizing link comes from alternative gravity models. Theories like modified Newtonian dynamics were crafted to explain galactic rotations without dark matter. but they also predict subtle deviations in how gravity behaves at cosmic scales. If these deviations affect inertia or the propagation of light, they could simultaneously explain Pioneer's odd motion and redshift anomalies. Imagine the universe as a vast, elastic sheet. Tug on one corner, and the ripple might distort measurements light years away. Skeptics argue that the Pioneer anomaly was eventually resolved mostly by accounting for heat radiation from the probe's power systems, but mostly leaves room for doubt. Residual discrepancies linger, and the broader lesson remains. Tiny, unmodeled forces can cascade into major observational puzzles. If we missed something as mundane as thermal radiation in our own solar system, what might we be overlooking in the redshift data? The universe rarely gives up its secrets easily. Sometimes the clues are hidden not in the distant cosmos, but in the quiet drift of a spacecraft closer to home, waiting for us to connect the dots. 10th on our list of cosmic conundrums is a phenomenon so bizarre it makes even seasoned astronomers double-check their date: binary stars that refuse to harmonize. These stellar pairs, locked in a gravitational dance, should move in perfect sync, their redshifts mirroring each other as they orbit a shared center of mass. Yet scattered across the cosmos are duos where one star's light stretches dramatically more than its partners, as if the universe handed them different sheet music. Take the case of Kaya-Zaminsky's star, a binary system where one member's redshift suggests it's racing away at breakneck speed while its companion sits nearly still. According to orbital mechanics, this shouldn't happen. If redshift purely reflected motion, both stars would share similar shifts, their mutual gravity dictating a balanced waltz. Dive into the data and the anomalies multiply. In systems like VV Cephei, the primary star shows a redshift inconsistent with its orbital velocity, while its massive companion follows the expected pattern. It's like watching two ice skaters holding hands, one gliding smoothly, the other inexplicably lurching ahead. Mainstream astronomy often chalks these mismatches up to atmospheric interference or measurement noise, but the consistency of the pattern across multiple systems raises eyebrows. Could something intrinsic to these stars, their composition, magnetic fields, or the seething plasma in their atmospheres, be imprinting extra redshift onto their light? Plasma physics offers one tantalizing clue. In labs, highly ionized gas plasma can redshift light passing through it without any motion involved. Stars, especially active ones, are swathed in churning plasma. If certain conditions amplify this effect, it might explain why some binaries show discordant redshifts. Picture two spotlights shining through fog. One beam passes through thin mist, barely dimmed, while the other cuts through a dense bank, emerging redder and fainter. No motion required. Critics argue that plasma redshifts, if real, would need impossibly dense or energetic conditions to match observed stellar anomalies. Yet similar mechanisms are already at work in quasars and active galactic nuclei, where plasma dynamics dramatically alter emitted light. If scaled-down versions of these processes occur in binary stars, they could resolve the mismatch without invoking cosmic expansion. The irony is thick. The same physics dismissed as fringe in one context is openly embraced in another. The stakes here are subtle but profound. If even a handful of binary redshifts stem from local plasma effects, it hints that our cosmic ruler might have invisible warps, places where light's stretching signals not the universe's expansion, but the hidden turmoil of stars themselves. When paired stars sing in discord, it's not just a technical glitch. It's a reminder that the cosmos often speaks in layers, and we're still learning how to listen. The 11th clue takes us into the seething hearts of galaxy clusters, where a phenomenon called the Sunyaev-Zeldovich effect reveals yet another crack in the cosmic expansion narrative. Here's how it works. As the faint glow of the cosmic microwave background, the afterglow of the Big Bang, passes through these clusters, hot electrons in the gas between galaxies scatter the photons, subtly distorting the background radiation in predictable ways. This distortion, named after the astrophysicists who first predicted it, has become a cornerstone for mapping the universe's largest structures. But buried in the data is a puzzle. Some clusters show distortions that don't quite match their redshifts, as if the gas itself is whispering secrets the models can't decipher. Take the massive cluster Abell 1689, a cosmic titan whose Sunyaev-Zeldovich signal suggests its gas should be hotter and more energetic than its redshift implies. According to standard cosmology, the cluster's redshift places it at a specific distance, and its gas dynamics should align neatly with that scale. Yet the observed effect hints at temperatures and pressures that defy expectations, like a furnace burning hotter than its fuel supply should allow. Similar mismatches appear in other clusters, where the scattering of microwave photons suggests gas behavior that doesn't neatly track with the assumed expansion rate. It's as if the universe handed us a recipe for galaxy clusters but forgot to include a key ingredient. One possible explanation lies in the turbulent, poorly understood physics of intracluster gas. These vast reservoirs of plasma, heated to millions of degrees, are anything but static. Magnetic fields twist through them, shock waves ripple from galactic collisions. Unseen turbulence could be imprinting extra energy onto the scattering photons. If the gas isn't in the tranquil equilibrium our models assume, the Sunyaev-Zeldovich effect might be picking up fingerprints of that chaos, fingerprints we've misread as redshift anomalies. Picture trying to measure the temperature of a boiling pot by listening to the bubbles. Without seeing the flames beneath, you might mistake the roiling noise for something else entirely. But there's a more provocative possibility that redshift itself isn't the pure cosmic ruler we've assumed. If part of a cluster's redshift stems from local processes, like the violent motion of gas or even unknown interactions between photons and the cluster's environment, it could mean the expansion signal we've attributed to the universe is partially a mirage. Some theorists, like astrophysicist Jean-Pierre Luminet, have speculated that the geometry of space-time within clusters might warp light in ways that mimic cosmological expansion without the actual stretching of space. Imagine looking through a funhouse mirror. The reflection seems stretched, but the object itself hasn't changed. The implications ripple far beyond galaxy clusters. If the Sunyaev-Zeldovich effect is revealing hidden layers in redshift story, it could mean our maps of the universe's large-scale structure, built on the assumption that redshift uniformly traces expansion, have subtle distortions woven into them. Skeptics argue that these mismatches are mere calibration issues, the growing pains of a young measurement technique. But when multiple independent surveys keep finding the same discrepancies, it's hard to dismiss as coincidence. The universe isn't just handing us answers, it's asking us to rethink the questions. And in the tangled dance of galaxy clusters, where light bends and redshifts waver, we might be glimpsing the first steps of a far more intricate cosmic ballet. The 12th clue plunges us into the heart of galaxies themselves, where the light from their spinning halos tells a story that defies simple expansion. Astronomers have long assumed that redshift should behave symmetrically across a galaxy's disk. One side spins toward us, blue shifting slightly, the other recedes, redshifting by an equal amount. But when researchers like Sofia Kahokos trained their spectrographs on spiral galaxies like M31, they found something unsettling. The redshifts between approaching and receding halves didn't balance out. Instead, the light from the far side often stretched more than expected, as if space itself were tugging harder on those photons. It's like watching a dancer twirl. One arm swings cleanly toward you while the other lags, weighed down by some unseen force. This asymmetry isn't just a curiosity, it strikes at the core of how we interpret cosmic motion. If redshift were purely a measure of uniform expansion, these imbalances wouldn't exist. Yet they persist across multiple galaxies, suggesting that local factors, turbulent magnetic fields, swirling plasma, or even the galaxy's own gravitational wake might be imprinting extra redshift onto escaping light. Take the case of NGC 2997, a spiral whose receding side shows redshift values up to 15% higher than its approaching half. Standard models chalk this up to kinematic noise, but the consistency of the pattern hints at something deeper. Imagine blowing bubbles through a straw. If the soap film on one side is thicker, the bubbles emerge distorted. Could the interstellar medium, the gas and dust between stars, be acting like that uneven film, warping light asymmetrically as it flees the galaxy? The implications ripple beyond individual galaxies. If halo asymmetries are common, they could subtly skew our measurements of cosmic expansion. Surveys that assume redshift uniformly traces motion might be conflating cosmological stretching with these local effects, like mistaking a river's current for the tide. Some theorists, like astronomer Margaret Burbidge, have speculated that intrinsic redshifts caused by energetic processes within galaxies could amplify the receding side's signal. Others point to dark matter's uneven distribution, which might gravitationally lens light in lopsided ways. Even the intergalactic medium, that sparse soup of ions filling the cosmos, could play a role if it interacts differently with light depending on its angle of escape. Mainstream cosmology often treats these asymmetries as minor corrections, noise to be filtered out, but critics argue that dismissing them risks painting an oversimplified picture of the universe's expansion. When the same anomalies recur across independent studies, from the Hubble Space Telescope's deep field images to ground-based surveys like SDSS, it's worth asking whether we're overlooking a fundamental piece of the puzzle. The universe rarely obeys clean symmetries. Maybe it's time we stopped expecting it to. So here's the challenge these galactic halos pose. If light carries hidden fingerprints of its journey through a galaxy's turbulent outskirts, how many other cosmic measurements might be quietly skewed? And if redshift isn't the impartial referee we assumed, what else have we misread in the cosmos's grand story? The 13th clue in our cosmic mystery unfolds in what astronomers call the redshift desert, a puzzling stretch of the universe where galaxies seem to vanish. Imagine combing through a vast forest, only to find a strange, empty clearing where trees should be. That's what happens when telescopes scan certain redshift ranges, expecting a steady distribution of galaxies, and instead hit eerie gaps. These deserts aren't just random voids, they appear at specific intervals, as if the cosmos has hidden blind spots where light refuses to cooperate. Take the gap near redshift 2.7, a stretch of the universe's timeline where galaxies become oddly scarce. Surveys like the Sloan Digital Sky Survey and the 2-degree field have mapped millions of galaxies, yet this desert persists. At first glance, it might seem like a simple observational fluke. Maybe dust clouds or instrument limitations are blocking our view. But the more astronomers refine their tools, the more the desert stubbornly remains. It's like trying to photograph a crowded stadium and finding the same empty seats no matter how many lenses you switch. One leading theory points to cosmic voids, those sprawling bubbles of near-nothingness stretching across the universe. If light from galaxies beyond these voids passes through them, it might be subtly stretched or dimmed in ways that shift their apparent redshifts into the desert range. Picture shouting across a canyon. Your voice might fade or echo, distorting how far away you sound. Similarly, voids could act as cosmic filters, warping our perception of galaxy distances. But here's the catch. Voids alone can't fully explain the desert's sharp boundaries or its recurrence at specific redshifts. Another possibility digs into the quirks of galaxy evolution. Around redshift 2.7, the universe was a turbulent adolescence with galaxies forming stars at breakneck speeds. Could something about this era, intense radiation, rampant black hole activity, have temporarily stifled galaxy formation, leaving behind a fossilized gap? Or perhaps the desert is a mirage, a selection effect caused by how light from certain distances interacts with Earth's atmosphere or telescope sensors. The Very Large Telescope in Chile, for instance, has spotted faint galaxies in the desert that older surveys missed, hinting that our tools might be painting an incomplete picture. But the most provocative idea is that the redshift desert isn't a flaw in our observations, it's a flaw in our assumptions. If redshift isn't always a clean measure of cosmic expansion, these gaps might trace back to unknown physics in the interstellar or intergalactic medium. Some theorists speculate that photon interactions with exotic particles or dark matter could selectively absorb or alter light at specific redshifts, creating artificial deserts in our maps. It's as if the universe has built-in filters, screening out certain wavelengths before they reach us. The stakes here are deceptively high. If the desert stems from mundane observational limits, it's a technical hurdle. But if it reflects something deeper, a wrinkle in how light travels or how structures form, it could mean our cosmic census is missing entire chapters of the universe's story. When galaxies vanish where they should thrive, it's not just a gap in the data. It's a silent challenge urging us to question whether we're reading the cosmos's signals or inventing patterns in the static. And in that silence, there might just be the whisper of a truth we haven't yet learned to hear. The 14th clue in our cosmic detective story takes us to one of nature's most mesmerizing illusions, gravitational lensing, where massive objects like galaxies bend the light of distant stars, creating multiple mirage-like images of the same object. It's a phenomenon Einstein himself predicted, a stunning confirmation of general relativity. But here's where the plot thickens. In some lensed systems, those duplicate images don't just appear at different positions, they show slightly different redshifts. It's like looking into a funhouse mirror and seeing not just warped reflections, but reflections that seem to age at different rates. Take the famous twin quasar, officially known as QSO 957+561. This distant beacon appears as two distinct images due to a foreground galaxy's gravity bending its light. Yet when astronomers measured their spectra, they found one image had a redshift subtly higher than the other. The difference was small, just a few parts in 10,000, but in the precise world of cosmology, even tiny discrepancies can signal something profound. If redshift purely marks cosmic expansion, lensed images of the same object should be identical, like twins wearing matching outfits, so why the mismatch? The usual suspects get rounded up first. Measurement errors, atmospheric interference, or subtle variations in the lensing galaxy's mass distribution could theoretically tweak the light's path enough to cause minor spectral shifts. But as more lensed systems revealed similar anomalies like SDSS-J 1106+439, where 4 images of a single quasar showed inconsistent redshifts, the case for mere noise grew thin. It's as if the universe were handing us identical puzzle pieces, each cut at a slightly different angle. One provocative explanation lurks in the physics of the lens itself. Could the lensing galaxy's halo of dark matter or turbulent plasma be imprinting extra redshift on some light paths? Picture a beam of sunlight passing through stained glass. The color changes depending on the glass's thickness and composition. Similarly, if certain photons graze denser pockets of interstellar gas or interact with exotic fields around the lens, they might emerge with added redshift, mimicking the effects of cosmic expansion. Some theorists, like physicist Hong-Sheng Zhao, suggest that dark matter's unknown properties might subtly alter light in ways we haven't accounted for, like invisible prisms bending rays to different degrees. Then there's the more radical possibility that space-time itself isn't as uniform as we assume. If the fabric of the cosmos has microscopic wrinkles or variations in its expansion rate, like a rubber sheet with uneven elasticity, light traversing different paths might accumulate slightly different redshifts. Imagine two hikers crossing a mountain. One takes a smooth trail, the other scrambles over rocks. Even if they cover the same distance, their journeys and their exhaustion won't match. Could photons, too, emerge from their cosmic trek with unequal fatigue? Skeptics counter that these anomalies are statistical flukes, artifacts of our still evolving lensing models. But when independent teams keep finding the same inconsistencies, like in the Hubble frontier fields, where lensed galaxy clusters show redshift mismatches, it's hard to dismiss as coincidence. The universe seems to be nudging us toward a humbling realization. That light, for all its elegance as a cosmic messenger, might carry hidden complexities we've only begun to decipher. So the next time you marvel at a gravitational lens, remember, those mirrored images aren't just cosmic curiosities. They're stress tests for our deepest assumptions about space, time, and the very meaning of redshift. And when the reflections don't quite align, it's not a flaw in the mirror. It's a clue waiting to be solved. 15th on our list of cosmic anomalies is a puzzle written in the oldest light we can see, the cosmic microwave background, or CMB. This faint glow, the afterimage of the Big Bang, has long been considered the ultimate proof of an expanding universe. Its subtle temperature fluctuations map the early cosmos with stunning precision, forming a blueprint that galaxies and clusters should follow as they grow. But when astronomers compare this ancient map to modern galaxy surveys, something unsettling emerges. The large-scale structures we see today, the sprawling filaments and voids of the cosmic web, don't align with the CMB's predictions as neatly as they should. It's like planting a garden using a detailed seed map, only to find the mature plants growing in subtly wrong places. Take the Sloan Digital Sky Survey, which has mapped millions of galaxies with painstaking accuracy. When researchers overlay these observations onto the CMB's primordial fluctuations, the match isn't perfect. Certain vast superclusters, like the Shapley concentration, appear more massive than the CMB's early density ripples can explain. Other regions, like the cold spot, a mysterious chill in the CMB spanning billions of light years, show fewer galaxies than expected, as if part of the universe forgot to fill in the dots. These mismatches aren't just academic quibbles. They hint that the universe's expansion might not be as uniform as our models assume. If the seeds planted in the CMB grew into today's structures exactly as predicted, the correlations would be airtight. Instead, we're left with gaps, places where the cosmic ledger doesn't quite balance. One glaring tension centers on the Hubble constant, the rate at which the universe expands. Measurements derived from the CMB, assuming standard cosmology, suggest one value. Yet galaxy surveys tracking the motions of supernova and other local markers consistently land on a higher number. It's as if the universe is expanding faster in our neighborhood than its primordial echo implies. Some theorists argue this discrepancy, known as the Hubble tension, could stem from unaccounted for physics in the early universe, perhaps a fleeting burst of dark energy or exotic particles that tweaked the expansion rate shortly after the Big Bang. Others propose more radical ideas, like a lumpy cosmos where expansion varies regionally, like dough rising unevenly in the oven. Then there's the curious case of the dipole anomaly. The CMB's temperature isn't perfectly uniform. It has a warm pole and a cool pole, a pattern traditionally attributed to our solar system's motion through space. But recent studies, like those analyzing the quasar catalog from the Gaia spacecraft, suggest this dipole might be far stronger than expected, or even aligned with entirely unrelated large-scale structures. If true, it could imply that the CMB's signal is being subtly distorted by something in the foreground, like a veil of undiscovered matter or a flaw in how we model the universe's geometry. Imagine tuning a radio and hearing two stations overlap. The static might hide a second signal waiting to be decoded. The most provocative possibility is that the CMB itself isn't the pristine relic we assume. What if foreground structures, cosmic filaments, invisible dark matter halos, or even primordial magnetic fields have imprinted extra patterns onto the microwave background, like fingerprints smudging a window? This wouldn't just tweak our maps, it could mean the CMB's redshift correlations are blending multiple epochs of cosmic history, with later structures whispering over the Big Bang's echo. Skeptics counter that the CMB's statistical significance is too robust for such contamination, but as anomalies pile up, the weight of the evidence grows harder to ignore. So what do these mismatches tell us? At their core, they're a challenge to the idea of a perfectly homogeneous expansion. If the universe's growth were smooth and unvarying, the CMB and galaxy surveys would lock together like gears. Instead, we're left with a puzzle where the pieces almost fit, but not quite. Whether the solution lies in new physics, hidden systematic errors, or a cosmic landscape far stranger than we've imagined, one thing is clear: the universe's story is still being written, and the CMB's whispers might be the first hints of chapters we haven't yet read. The 16th clue in our cosmic puzzle isn't just about snapshots of the universe, it's about watching it age in real time. Imagine if you could take a photograph of the night sky today, then another in 20 years, and compare them like pages in a flipbook. That's the essence of redshift drift, a cutting-edge technique where astronomers measure how the stretching of light from distant galaxies subtly shifts over decades. It's a staggeringly ambitious idea, tracking the universe's expansion not through indirect clues, but by witnessing its motion frame by frame, and the early results. They're hinting at a plot twist no one saw coming. The logic seems straightforward. In an evenly expanding universe, redshift should change predictably over time, like a car's engine humming at a steady RPM. But when teams like those behind the Keck and Very Large Telescope surveys began comparing quasar spectra from the 1990s to modern observations, they caught whispers of something stranger. A handful of these cosmic beacons showed redshift changes that didn't quite match the expected pace, as if the universe had tapped the brakes or the gas in certain regions. Take Quasar 3C273, whose redshift drift over 25 years was slightly slower than Lambda CDM, the standard model of cosmology, would predict. It's a tiny deviation, barely a blip in the data. But in the high-stakes game of cosmic measurement, even blips can be seismic. What makes these anomalies so provocative is their implication. The universe's expansion might not be as smooth as we've assumed. Current models treat dark energy, the mysterious force accelerating cosmic growth, as a constant, like a steady wind filling the universe's sails. Yet if redshift drift reveals patches where expansion speeds up or slows down unexpectedly, it could mean dark energy itself fluctuates, pulsing through space in waves we've yet to map. Picture a river that sometimes races, sometimes trickles, its current dictated by hidden underground springs. That's the kind of cosmos redshift drift might be unveiling, one where expansion isn't a monotonous drumbeat, but a symphony with movements we're only beginning to hear. Critics argue these early drift measurements are still too crude to upend cosmology. Atmospheric interference, instrumental limits, and the sheer difficulty of tracking infinitesimal spectral shifts across decades leave room for doubt. But proponents counter that the anomalies persist across independent datasets, like the Sloan Digital Sky Survey's Quasar catalog, which shows similar mismatches in a subset of objects. Even more tantalizing are models like Quintessence, which propose dark energy isn't a static force but a dynamic field that ebbs and flows. If redshift drift eventually confirms such ideas, it wouldn't just tweak our equations, it would rewrite the universe's biography, revealing chapters where expansion stalled or surged in ways we never anticipated. The real magic of this clue lies in its patience. Unlike fleeting supernova or static galaxy maps, redshift drift demands a generational perspective, a willingness to plant observational seeds today that might only bear fruit decades hence. It's a reminder that cosmology isn't just about decoding the past, it's about stepping into the role of cosmic historians, chronicling the universe's unfolding story in real time. And if the early whispers of drift are any indication, that story might be far richer, far wilder than we've dared to dream. 17th in our lineup of cosmic enigmas is a phenomenon that seems to defy the universe's very script, the baffling existence of blue-shifted objects. In a cosmos supposedly stretching apart at every point, where redshift reigns supreme, these rare outliers glow blue, their light compressed as if racing toward us against the cosmic tide. Take the Andromeda Galaxy, our Milky Way's neighbor, hurtling closer with a blue shift that's easy to dismiss as local motion. But venture deeper into the cosmic ledger, and you'll find anomalies like Galaxy Messier 86, drifting through the Virgo cluster with a blue shift that defies the cluster's overall retreat. It's like spotting a lone swimmer charging upstream while the entire river flows the other way. The immediate explanation is simple: peculiar velocity. Just as a leaf might whirl against a river's current, galaxies can have local motions that overpower the universe's expansion. But dig into the data and contradictions emerge. Some blue-shifted objects, like certain quasars, sit so far away that their apparent motion toward us would require speeds beyond what gravity alone can explain. Then there's the case of the Bullet Cluster, where colliding galaxies create shockwaves of hot gas, some blue-shifted, some red-shifted in patterns that don't neatly fit conventional models. It's as if the universe scribbled outside the lines, leaving us to decipher the smudges. Could these blue shifts hint at something beyond local chaos? One radical theory suggests they might trace back to cosmic recoil regions where space itself briefly snaps back like a stretched rubber band. Picture the aftermath of a colossal collision between galaxy clusters. The gravitational shockwaves might ripple through space-time, creating temporary pockets where expansion reverses. Alternatively, blue shifts could emerge from light interacting with exotic fields or dark matter structures, its wavelength tweaked by unseen forces. Even more provocative is the idea that some high-energy objects, like active galactic nuclei, might emit light with intrinsic blue-shift components, a sort of cosmic Doppler effect in reverse. Skeptics argue that these are all measurement glitches, dust clouds bending light, instrumental noise, or the simple statistical inevitability of outliers in vast datasets. But when surveys like the Hubble Space Telescope's deep-field observations keep finding blue-shifted galaxies in regions where they shouldn't exist, the anomalies demand a second look. Science thrives on exceptions, and these cosmic rebels, whether flukes or fractures in our models, remind us that the universe's rulebook might still have pages left to unfold. So the next time you hear that the cosmos is expanding everywhere, remember, somewhere out there, a few stubborn dots of blue refuse to go with the flow. And in their defiance, they might just hold the key to a deeper truth. The 18th clue in our cosmic mystery unfolds not in the isolated quirks of galaxies or clusters, but in the vast, sweeping patterns etched across the entire sky. When astronomers map redshift distributions on the grandest scales, piecing together surveys like the Sloan Digital Sky Survey or the Dark Energy Spectroscopic Instrument, they expect a roughly even tapestry, a universe that looks the same in all directions. That's the cosmological principle in action, the bedrock assumption that the cosmos is homogeneous and isotropic when viewed at large enough scales. But the data tells a different story. In certain patches of the sky, redshifts cluster more densely, as if the universe's expansion is subtly uneven, like a balloon inflating faster on one side than the other. Take the so-called axis of evil, a controversial alignment first spotted in the cosmic microwave background. This faint but persistent pattern suggests the early universe might have had a preferred direction, a cosmic north that defies the principle of uniformity. Fast forward to modern galaxy surveys, and similar anisotropies emerge. In one hemisphere, galaxies might show slightly higher redshifts on average than their counterparts in the opposite direction. The differences are minuscule, often less than 1%, but in a field where precision is everything, even tiny deviations raise eyebrows. It's like surveying a forest and finding the trees on the east side consistently taller than those on the west, despite identical soil and climate. The implications ripple through cosmology. If these anisotropies are real, they could hint at something monumental, that the universe's expansion isn't perfectly uniform after all. One possibility is that we're seeing the fingerprints of colossal, unseen structures, supervoids or superclusters, so vast they warp the fabric of space-time on scales we've barely begun to map. Picture a room where the floor tilts imperceptibly. Drop a marble and it rolls ever so slightly toward the dip. Similarly, light traversing these cosmic troughs or ridges might emerge with redshifts subtly tweaked by the journey. But there's a more radical interpretation, that the cosmological principle itself might need revision. For centuries, science has clung to the idea that the universe has no special place or direction, that every observer, no matter where they stand, sees roughly the same cosmos. Yet if redshift anisotropies persist across independent surveys, it could mean our universe resembles not a perfectly smooth dough, but a loaf with hidden seams, where expansion tugs harder in some regions than others. Some theorists, like astrophysicist Subir Sarkar, argue that these patterns might trace back to the universe's birth, relics of primordial asymmetries that never fully smoothed out. Skeptics counter that these anisotropies are statistical mirages, artifacts of incomplete sky coverage or systematic errors in how we measure distances. After all, Earth isn't a perfect vantage point. Dust in our own galaxy, the motion of the solar system, even the gravitational pull of nearby galaxy clusters could subtly skew our maps. But as surveys grow more precise, like ESA's Euclid mission, mapping billions of galaxies across the sky, the anomalies refuse to vanish. If anything, they grow sharper, like a faint radio signal slowly tuning into focus. So here's the dilemma these sky-wide patterns pose. Do they reflect the universe's messy, lumpy adolescence, a phase it hasn't quite outgrown? Or are they cracks in the foundation of cosmology itself, hints that the universe's rulebook isn't as universal as we thought? The answer might lie not in the anomalies we've found, but in the ones still hiding in the data, waiting for the next generation of sky surveys to bring them into the light. 19th on our list of cosmic conundrums plunges us into the electrifying world of plasma cosmology, a radical reimagining of the universe where swirling currents of ionized gas, not gravity alone, sculpt the cosmos. While mainstream astronomy treats redshift as the gold standard for measuring expansion, plasma physicists argue we've been missing a crucial player, the seething, magnetic dance of plasma that fills interstellar space. Picture the universe not as a serene expanse of drifting galaxies, but as a cosmic circuit alive with currents, where filaments of charged gas stretch across millions of light-years, capable of bending light in ways that mimic or mask cosmic expansion. At the heart of this alternative vision stands Hans Alfvén, the Nobel-winning physicist who championed plasma's role in shaping the universe. His work revealed how plasma, the same stuff that fuels stars and lightning, can generate redshift without a single inch of space stretching. In lab experiments, plasma under intense magnetic fields shifts light's wavelength, not through motion, but through interactions with its own turbulent structure. Now scale that up to galactic proportions. If intergalactic space crackles with faint plasma currents, could they be imprinting extra redshift onto distant starlight? It's like mistaking the red glow of a neon sign for a receding light bulb. The color might signal local physics, not cosmic flight. The implications are staggering. Take quasars, those high redshift enigmas. Plasma cosmology suggests their extreme redshifts might not reflect distance, but the dense magnetized plasma surrounding them, a natural byproduct of their violent birth. Similarly, the quantized redshifts we discussed earlier could trace back to plasma's preference for specific energy states, like electron jumps in an atom. Even the Sunyaev-Zeldovich effect, where galaxy clusters distort microwave background radiation, might carry hidden plasma fingerprints. Mainstream models attribute these distortions solely to hot gas, but plasma theorists argue magnetic fields and current sheets could amplify the effect, subtly skewing our redshift measurements. Critics dismiss plasma cosmology as a fringe distraction, pointing out that the universe's large-scale structure aligns too neatly with gravitational models to credit plasma as a dominant force. Yet the anomalies persist. Why do some galaxy clusters show redshift discrepancies that align with their plasma-rich environments? Why do active galaxies with powerful jets, regions teeming with magnetized plasma, often exhibit anomalous redshifts? The answers might lie in a middle ground. Perhaps plasma doesn't replace cosmic expansion, but complicates it, adding noise to a signal we've treated as pristine. What makes this clue so provocative isn't just the science, it's the philosophical divide it exposes. Mainstream cosmology prizes simplicity, favoring the clean elegance of universal expansion. Plasma cosmology embraces complexity, arguing that the universe is a messy, electrified tapestry where multiple forces sculpt light's journey. Both can't be wholly right, but what if both hold pieces of the truth? The next time you gaze at a redshift map of the cosmos, remember, those stretched wavelengths might be more than just a cosmic speedometer. They could be a palimpsest, layers of expansion, plasma, and something stranger still, waiting to be peeled apart. The 20th clue brings us to the heart of modern cosmology's greatest crisis, the Hubble tension, a stubborn rift in how fast we think the universe is expanding. On one side, measurements anchored in the cosmic microwave background, that ancient echo of the Big Bang, suggest a precise expansion rate. On the other, observations of nearby supernova and galaxies land on a noticeably faster value. The gap between them isn't just a rounding error, it's a chasm wide enough to shake the foundations of astrophysics. But what if the answer has been hiding in plain sight, tangled in the very redshift anomalies we've been exploring? Take the local measurements where astronomers use Type Ia supernova as cosmic yardsticks. Their redshift should correlate neatly with distances, painting a consistent picture of expansion. Yet, as we've seen, some supernova defy expectations, shining brighter or dimmer than their redshifts predict. If even a fraction of these outliers owe their mismatches to overlooked intrinsic redshifts, perhaps from turbulent plasma environments or unmodeled gravitational effects, it could mean our local Hubble constant is subtly skewed. Imagine trying to measure a room's dimensions with a tape measure that occasionally stretches or shrinks. Your numbers might disagree with someone using a laser level, even if both tools are mostly reliable. Now zoom out to the cosmic microwave background's perspective, where redshift serves as a pristine tracer of the universe's early expansion. Here, the anomalies take a different form. The CMB's redshift correlations assume a perfectly homogeneous cosmos, but as we've uncovered, large-scale structures, voids, filaments, even redshift deserts might imprint extra patterns onto the light. If these structures add noise to the CMB's redshift signal, our inferred expansion rate could be off by just enough to fuel the tension. It's like listening to a symphony through a wall. The music's still there, but the muffling might make the tempo seem slower than it is. The most tantalizing possibility is that both camps are partly right and partly wrong. Local measurements might conflate cosmic expansion with local astrophysical redshifts, while CMB analyzers could be mistaking structural imprints for uniform growth. This isn't just splitting the difference, it's acknowledging that redshift, the backbone of cosmic distances, might be a more complex beast than we assumed. Some theorists, like physicist David Wiltshire, argue that cosmic voids, those vast, underdense regions, could slow light in ways that mimic faster local expansion. Others propose that dark energy's influence isn't uniform, creating pockets where redshift behaves unpredictably. The stakes couldn't be higher. If redshift anomalies are papering over a fundamental flaw in our models, resolving the Hubble tension might require more than tweaking parameters. It could demand a paradigm shift. Yet there's hope in the chaos. Every mismatch, every deviation we've explored, from quantized redshifts to lensing anomalies, offers a potential thread to pull, a way to disentangle the universe's true expansion from the artifacts we've mistaken for truth. The Hubble tension isn't just a crisis, it's an invitation to look deeper, to question not just our answers, but the very tools we've used to find them. And in that questioning, we might finally hear the universe's unvarnished story. The 21st clue in our cosmic puzzle isn't just about how galaxies move, it's about how entire clusters of them seem to be pulled by something beyond the visible universe. Astronomers call it dark flow, a mysterious river of motion where thousands of galaxy clusters drift in the same direction at blistering speeds, as if tugged by an invisible hand. This isn't just random cosmic drift. These clusters share a common trajectory, racing toward a point in the sky near the constellations Centaurus and Vela. And here's where it gets eerie. Some of these racing clusters show redshift anomalies that don't quite match their expected velocities, like speedometers stuck between two readings. Take the work of Alexander Kashlinsky and his team, who first spotted dark flow in data from the Wilkinson microwave anisotropy probe. They found galaxy clusters hurtling at over 600 kilometers per second toward the same distant attractor, far faster than standard cosmology can explain. But when researchers cross-referenced these motions with redshift measurements, discrepancies emerged. Some clusters in the flow had redshift slightly higher or lower than their surroundings, as if their light had been stretched or squeezed by something other than expansion. It's like watching a school of fish swimming against the current, only to notice some of them flicker oddly, their colors out of sync with the rest. What could explain this? One radical possibility is that dark flow isn't just a quirk of gravity. It's a sign of something outside our observable universe exerting its pull. Imagine standing in a room where all the curtains are drawn shut. If you notice a steady breeze, you might suspect an open window beyond your view. Similarly, if galaxy clusters are being dragged by mass beyond the cosmic horizon, their redshifts might carry fingerprints of that unseen influence. Some theorists speculate this could be evidence of a neighboring universe in the multiverse, its gravity leaking into ours like sound through a wall. Others propose it's a relic of the pre-Big Bang era, a cosmic undertow left over from the birth of space-time itself. Then there's the redshift connection. If dark flow is real, it could mean that some portion of the redshifts we attribute to cosmic expansion might actually stem from these bulk motions. Picture a boat drifting downstream while also caught in a whirlpool. Its movement isn't just about the river's flow. Similarly, galaxies in these racing clusters might have their light stretched not only by the universe's expansion, but also by the extra velocity of the dark flow. This would add noise to our redshift measurements, subtly distorting our cosmic yardstick. Studies like those using the Planck satellite have tried to dismiss dark flow as statistical noise, but the signal persists in deeper surveys, whispering that we might be missing a piece of the puzzle. The implications are staggering. If redshifts can be tweaked by external forces, it would mean our map of the universe's expansion is like a compass near a magnet, still useful but subtly skewed. Skeptics argue that dark flow could simply trace back to enormous, unseen structures within our own cosmos, like superclusters weaving a gravitational web. Yet even that explanation would require a rewrite of how matter is distributed on scales we've never probed. Whether the culprit is a hidden universe, primordial turbulence, or something stranger, dark flow challenges the tidy story of a cosmos expanding evenly in all directions. So the next time you hear that the universe is stretching like a rubber sheet, remember, there might be hands tugging at the edges, warping the fabric in ways we're only beginning to sense. And in that tension between what we see and what we almost see lies a clue that could redefine not just our universe, but our place within it. The 22nd clue in our cosmic detective story doesn't just tweak the rules, it rewrites them entirely. Enter modified gravity theories, like modified Newtonian dynamics, a radical framework suggesting that gravity behaves differently on galactic scales than Einstein's equations predict. While mainstream cosmology leans on dark energy and dark matter to explain redshift anomalies, MUND and its cousins propose a startling alternative. Maybe we've misread the universe's expansion because we've misunderstood gravity itself. Picture a car skidding on a wet road. Standard physics says the tires lost traction, but what if the road itself changed texture in ways the driver couldn't see? That's the essence of MUND's approach to redshift. Instead of invoking invisible dark energy to explain why galaxies recede faster than expected, MUND suggests that gravity's pull weakens less sharply over vast distances than Newton or Einstein predicted. This subtle tweak to the math, introduced by physicist Mordechai Milgrom in the 1980s, could explain why some galaxies rotate too fast for their visible mass, or why certain redshift patterns cluster oddly, without needing dark matter's invisible scaffolding. Take the pioneer anomaly we discussed earlier, those spacecraft mysteriously slowing down as they left the solar system. While some blamed thermal radiation, MUND proponents saw a hint of deeper physics. If gravity's grip doesn't fade as sharply as we thought at low accelerations, it could explain the probe's deceleration and certain galactic redshift mismatches in one stroke. Similarly, quantized redshifts, those eerie, ladder-like patterns in galaxy clusters, might trace back to gravity's modified behavior, creating preferred energy states, like rungs on a cosmic energy ladder. But the real test lies in the Hubble tension. and revised gravity could, in theory, reconcile the conflicting expansion rates measured locally versus in the CMB by altering how light's redshift accumulates over cosmic distances. Imagine two runners on a track where the lanes subtly widen or narrow. Their speeds might seem mismatched unless you account for the shifting terrain. If gravity's strength varies with scale or environment, redshift might not uniformly trace expansion, offering a way out of the tension. Critics counter that and struggles to explain the universe's largest scale structures, like the cosmic web's filamentary patterns, which dark matter models nail beautifully. Yet even here, redshift anomalies creep in. Some galaxy surveys show filaments with redshift distributions that, like theories, actually predict better than standard cosmology, particularly where gravity's tweaked behavior would warp light's journey differently. It's as if the universe left two sets of blueprints, one for dark matter, one for modified gravity, and we're only now noticing the discrepancies, the boldest implication. Dark energy might not just be mysterious, it could be unnecessary. If gravity's modified pull accounts for redshift patterns sans expansion, the need for a universe-wide repulsive force evaporates. Of course, this isn't a settled debate, and has its own gaps, like explaining the CMB's precise fluctuations. But the sheer fact that alternative gravity can match some redshift anomalies mainstream models fumble suggests a humbling truth. Our cosmic map might have more than one key. So here's the choice these theories force upon us. Do we keep grafting invisible ingredients onto our equations to preserve Einstein's gravity, or do we reconsider the equations themselves? When redshift data whispers contradictions, it's not just challenging dark energy, it's asking whether we've been reading the universe's deepest language with the wrong dictionary. And in that question lies the thrill of science. The rules aren't sacred, only the evidence is. The 23rd clue in our cosmic mystery unfolds like a time lapse of the universe itself, where redshift isn't just a snapshot of expansion, but a film strip revealing how galaxies' light evolves over billions of years. Imagine flipping through a family photo album, expecting each generation to age predictably, only to find certain relatives inexplicably changing hair color or height at random intervals. That's the enigma astronomers face when they trace redshift distributions across cosmic epochs. According to standard models, as the universe expands, older galaxies at higher redshift should show smoother, more primitive features, like fossils preserving the early universe's conditions. Yet when telescopes like James Webb peer back to these ancient eras, they catch galaxies with redshift patterns that don't just reflect passive aging, but active, almost rebellious transformations. Take the so-called redshift desert around redshift 2, a period roughly 3 to 4 billion years after the Big Bang, where galaxies abruptly shift their spectral signatures. Surveys like VMO's VLT Deep Survey reveal that galaxies in this epoch don't just fade into the background. Their redshifts cluster in unexpected ways, with some showing stronger absorption lines from elements like magnesium or sodium than their modern counterparts. It's as if the universe hit a cosmic growth spurt during this era, with galaxies churning out stars and metals at rates that leave unusual fingerprints in their light. Even more puzzling are redshift spikes, narrow windows of time where galaxies at specific redshifts appear more massive or chemically enriched than their neighbors, like finding a medieval castle suddenly outfitted with steel beams. Could these anomalies trace back to galaxy evolution alone? One camp argues yes, that bursts of star formation or supermassive black hole activity might temporarily alter how galaxies emit light, imprinting extra redshift or blueshift components onto their spectra. Picture a forest where some trees grow faster during wet seasons, their rings thickening disproportionately. Similarly, galaxies in certain epochs might have undergone violent growth spurts, their light reflecting that turbulence. But others see a deeper cosmological thread. If redshift evolution doesn't align neatly with galaxy life cycles, might it hint at fluctuations in the universe's expansion rate itself? Some theorists propose that dark energy, the force driving cosmic acceleration, wasn't always constant. Brief surges in its strength could have stretched space-time unevenly, leaving redshift distributions skewed like bread dough proofed at varying temperatures. The most tantalizing data comes from quasars, those brilliant beacons whose redshifts span nearly the universe's entire history. When astronomers like Martin Schmidt compared ancient quasars to younger ones, they found a curious pattern. The oldest quasars often show cleaner spectral lines, as if the intergalactic medium they're shining through was less cluttered early on. Yet their redshifts don't always track this purification smoothly. Instead, certain eras like redshift 3 to 4 show abrupt drops in absorption features, as if the universe had episodic cleaning events where vast regions were swept free of gas. These quirks defy the steady, homogenizing expansion predicted by lambda CDM, the standard model of cosmology. Skeptics counter that observational biases, like telescopes being more sensitive to certain redshifts, could create artificial patterns. But as datasets grow, the anomalies persist. The Legacy survey, mapping galaxies at redshift 0.7, found stellar motions that imply gravity behaved slightly differently in that era, subtly distorting redshift measurements. Similarly, the ALMA telescope's deep scans of ancient dust clouds reveal chemistry that doesn't quite match what redshift-based age estimates predict. It's as if the universe's clock ticks irregularly in places, its expansion history written with invisible ink that only certain observations can reveal. What makes this clue so transformative is its duality. Redshift evolution could be both a cosmic odyssey, a record of the universe's growth, and a hall of mirrors where galaxy physics and cosmology refract each other's signals. The answer might lie not in choosing one over the other, but in untangling their dance. When ancient light reaches us, stretched by expansion and sculpted by eons of stellar violence, it carries not just a message from the past, but a challenge to read between the wavelengths where the universe's secrets hide in plain sight. What if the key to redshift's deepest mysteries lies not in the vast emptiness of space, but in the subatomic flicker of quantum foam? The 24th clue catapults us into the mind-bending realm of quantum gravity, where the fabric of reality itself might be warping light in ways Einstein never imagined. Picture the universe not as a smooth, stretching sheet, but as a seething quantum ocean where space-time bubbles with microscopic fluctuations so violent they could subtly tint the light traveling through them. This isn't just theoretical musing. It's a frontier where redshift might not solely mark cosmic expansion, but carry echoes of the universe's tiniest vibrations. Loop quantum cosmology, a radical offshoot of quantum gravity, offers one tantalizing possibility. In this framework, space-time isn't infinitely divisible. It's woven from tiny, indivisible loops, like a cosmic tapestry stitched at the Planck scale. As light traverses this pixelated landscape, its wavelength could stretch or compress depending on the quantum terrain, adding an extra layer of redshift unrelated to expansion. Imagine a hiker crossing a mountain range. Their stride lengthens in valleys and shortens on peaks. Similarly, photons might feel the texture of quantum spacetime, emerging with spectral shifts that masquerade as cosmic motion. Some models even predict redshift quantization, those eerie, stair-stepped patterns we've observed, as natural fallout of spacetime's granular structure. Then there's the holographic principle, the audacious idea that our three-dimensional universe might be a projection of information encoded on a distant, two-dimensional surface. If true, light's journey through the cosmos could be akin to a film reel projected onto a warped screen, with redshift reflecting not just expansion, but distortions in the projector. Studies like those by physicist Sunyaev-Zeldovich suggest this could explain anomalies like the CMB's odd large-scale patterns, where certain redshift correlations align with holographic entanglement entropy, a measure of quantum connections across cosmic distances. It's as if the universe's redshift map carries a watermark, a hidden signature of its holographic origins. The most provocative evidence comes from black hole physics. When matter falls into a black hole, its light redshifts to infinity, a phenomenon long attributed to extreme gravity. But quantum gravity theories propose that near the event horizon, spacetime's discrete nature might imprint additional redshift components, like static on a radio signal tuned to the edge of reality. If similar quantum effects leak into intergalactic space, perhaps via dark matter interactions or primordial spacetime defects, they could subtly alter redshift measurements across the cosmos. Telescopes like the James Webb might already be catching whispers of this. Certain high-redshift galaxies show spectral lines with asymmetries that resist conventional explanations, as if their light grazed quantum structures on its way to us. Critics argue these ideas flirt with untestable speculation, that quantum gravity's domain is too small to visibly influence galaxy-scale redshifts. Yet defenders counter that quantum effects needn't stay microscopic. Cosmic inflation, the universe's explosive infancy, could have stretched quantum fluctuations to astronomical scales, freezing them into the fabric of space like fossils in amber. If so, redshift anomalies might be the archaeological remains of a quantum past waiting to be decoded. The challenge and the thrill lies in designing experiments to tease apart these signals. Proposals range from hunting for redshift correlations in ultra-precise quasar surveys to probing the cosmic microwave background for fingerprints of spacetime's granularity. What makes this clue so transformative isn't just its audacity, but its potential to unify redshift's contradictions. Quantum gravity doesn't erase cosmic expansion, it complicates it, offering new lenses to interpret the data. Perhaps dark energy's acceleration is really quantum pressure, or redshift deserts trace back to spacetime's pixelation. The universe has never been one for simple answers. As we peer deeper into the quantum shadows, we might find that light stretching isn't just a measure of the cosmos's growth, but a cipher encoding the secret language of reality's smallest scales. And in that cipher, the next revolution in cosmology could be waiting. The 25th clue in our cosmic mystery shifts the lens from the vast expanse of the universe to something far more intimate, our own existence within it. The anthropic principle, that controversial idea suggesting the universe's laws appear fine-tuned to allow life like ours, might hold unexpected clues about redshift's deepest puzzles. What if the anomalies we've been chasing, those mismatched galaxies, quantized patterns, and drifting supernova aren't just random glitches, but subtle signatures of a cosmos tailored for observers? Imagine walking into a library where every book just happens to be written in your native language. You might assume it's coincidence, or you might wonder if the library was built with you in mind. Take the cosmic microwave background's near-perfect uniformity, a fingerprint of the early universe's conditions. Its temperature varies by less than 1 part in 100,000. A balance so precise that even slight tweaks would have left the cosmos barren. Now zoom in on redshift. Its very reliability as a distance marker hinges on constants like the speed of light and Planck's energy scale's values that, if altered by a hair, would render the universe unrecognizable. But here's the twist. What if life-friendly physics requires redshift to behave in ways that occasionally defy our models? Some theorists, like astrophysicist Brandon Carter, argue that certain anomalies might arise because we're observing the universe from a privileged niche where conditions allow complex life. Consider the redshift deserts we explored earlier, those eerie gaps where galaxies vanish at specific redshifts. From a purely statistical view, there are flaws in the data. But through an anthropic lens, they might trace back to eras where star formation was suppressed by intense radiation, preventing lethal gamma-ray bursts from sterilizing nascent life. Similarly, the Hubble tension's conflicting expansion rates could reflect a cosmic Goldilocks zone: too fast and galaxies never form, too slow and the universe collapses before life emerges. Our observational perch, a stable galaxy in a late-era universe, might filter redshift data in ways we're only beginning to decipher. This isn't just philosophical musing. Studies like those by physicist Anthony Aguirre highlight how life-compatible universes might favor certain redshift distributions. In multiverse scenarios where countless universes bubble with different physical laws, observers like us would inevitably find ourselves in one where redshift mechanics permit galaxies, and thus planets, to exist. The quirks we spot, like quasars without time dilation or clustered redshifts, could be artifacts of this selection effect. Picture a fish puzzling over why water is transparent. It's the only environment where fish can ponder. Similarly, we might be seeing redshifts, oddities, simply because they're the ones compatible with our existence. Critics dismiss this as circular reasoning, a cosmic just-so story. Yet the data nudges back. The fine structure constant, which governs light's interaction with matter, appears eerily tuned for chemistry that supports life. If this constant varied even slightly, redshift measurements would drift unpredictably, rendering cosmology impossible. Even dark energies mysteriously tiny but non-zero value. The engine of cosmic acceleration fits the anthropic sweet spot, enough to drive galaxy formation, not so much to tear them apart. The most humbling implication: redshift might not be a pure cosmic ruler after all, but a local dialect, a measurement flavored by the very conditions that allow us to make it. When we map the universe's expansion, we're not just reading its history, we're seeing the shadow of our own existence. And in that shadow, there might lie answers to why the cosmos refuses to follow the script we've written for it. The anomalies we chase could be more than errors in our equations. They might be messages from the universe, whispering that the rules we've crafted are just one page in a much stranger story. The 26th clue catapults us beyond the edges of our known universe into the dizzying realm of the multiverse, where alternate realities with alien physics might be subtly warping the redshift data we see. Picture a hall of mirrors, each reflecting a slightly distorted version of reality, their boundaries pressing against our own. If even a fraction of these neighboring universes leak gravitational influence or collide with ours, their fingerprints could linger in the anomalous redshifts we've been cataloging. It's not just science fiction. Leading theories like eternal inflation suggest our cosmos might be one bubble in an endless froth of universes, each with its own laws. And where those bubbles brush against each other, the fabric of space-time might ripple in ways that skew the light passing through. Take the cold spot in the cosmic microwave background, a vast, inexplicably chilly region spanning nearly 2 billion light-years. Some theorists, like Laura Mersini-Horton, argue it could be a bruise from a collision with another universe, its gravity tugging on ours during the Big Bang's aftermath. If true, that cosmic crash might have left secondary imprints in redshift distributions, subtly altering how galaxies recede in that direction. Surveys like the Dark Energy Survey have found peculiar galaxy flows near the cold spot, their redshifts ever so slightly off-kilter from surrounding regions. It's as if the universe's canvas has a warp woven into it, invisible unless you know where to look. But the multiverse's potential signatures don't stop there. In string theory's landscape, where countless universes flicker into existence with different physical constants, some might harbor stronger or weaker dark energy, a variation that could leave redshift anomalies at their boundaries. Imagine two soap bubbles merging. The surface where they meet isn't perfectly smooth. Similarly, if our universe borders one where dark energy is stronger, galaxies near that invisible frontier might show redshifts that accelerate unnaturally fast, like cars suddenly hitting an unseen slope. Astronomers have already spotted peculiar bulk flows, vast streams of galaxies moving in unison that exceed predicted velocities. Could these be the wake of a neighboring universe's gravity lapping at ours? The most tantalizing hints come from quantized redshifts, those mysterious stair-stepped patterns in galaxy distributions. In a multiverse scenario, these could reflect resonant frequencies between universes, like harmonics vibrating across a shared membrane. If space-time has a granular structure at cosmic scales, as loop quantum gravity suggests, interactions with parallel realities might tune redshift values to preferred intervals. It's the cosmic equivalent of plucking a guitar string and hearing the same note echo from a second, hidden instrument. Even the Hubble tension, the rift in expansion rates, might find resolution if our local neighborhood is nudged by a nearby universe's gravity, subtly altering how we measure distances. Critics dismiss these ideas as untestable speculation, arguing that multiverse theories are a kitchen sink for unexplained phenomena. But defenders counter that precision cosmology is now sensitive enough to spot statistical anomalies like correlated galaxy orientations or redshift asymmetries that could betray external influence. Future telescopes like the ESA's Euclid or NAS, a Roman space telescope, might hunt for these fingerprints by mapping billions of galaxies in 3D, searching for patterns that defy conventional physics. The irony is profound. The very tool we've used to map our universe's expansion redshift might someday reveal that our cosmos isn't alone. Whether these anomalies stem from cosmic neighbors, quantum entanglement between universes, or entirely new physics, one thing is clear. The redshift data we've trusted as a yardstick might be a Rosetta Stone, waiting to decode realities beyond our own. And if that's true, every mismatch in our models isn't a flaw, it's a window. The 27th clue isn't just about the mysteries we've uncovered. It's about the ones waiting to be revealed, hidden in the flood of data from a new generation of cosmic observatories. At the forefront is the Vera Rubin Observatory, a revolutionary telescope perched in Chile's Atacama Desert, set to begin its legacy survey of space and time in 2025. With a camera the size of a small car and the ability to scan the entire southern sky every few nights, Rubin will capture redshifts for billions of galaxies, quasars, and supernova with unprecedented precision. This isn't just an upgrade, it's a cosmic microscope, sharpening our view of the universe's expansion to a clarity we've never had. And if history is any guide, sharper vision often reveals surprises. Consider how past telescopes rewrote the cosmic playbook. Edwin Hubble's observations at Mount Wilson in the 1920s shattered the static universe myth by revealing redshifts that pointed to expansion. The Sloan Digital Sky Survey, decades later, exposed the cosmic web's filamentary structure, proving the universe wasn't just expanding, it was growing in intricate, unexpected patterns. Now Rubin and its peers like ESA's Euclid and NAS, a Nancy Grace Roman Space Telescope, are poised to take the next leap. But here's the twist. These instruments aren't just tools to confirm existing theories. They're engines of discovery, calibrated to expose the very anomalies that could dismantle them. One tantalizing target is redshift drift, the subtle shift in galaxies' spectral lines over time. While current telescopes can barely detect this effect, Rubin's decade-long survey will track it across millions of objects, testing whether dark energy's acceleration is as constant as we've assumed. Early simulations suggest the data might reveal kinks in the expansion rate, brief epochs where the universe's growth sped up or slowed down unexpectedly. Imagine graphing a car's speed during a road trip and finding stretches where the odometer flickered erratically, despite the pedal being steady. Such deviations could hint at dark energy's dynamic nature, or even entirely new physics woven into the fabric of space-time. Then there's the enigma of large-scale anomalies. Rubin's wide-field imaging will map galaxy distributions with pixel-perfect accuracy, probing whether redshift deserts, bulk flows, and other cosmic oddities are statistical flukes or fundamental features. Take the controversial axis of evil, that eerie alignment in the CMB suggesting a preferred direction in the universe. Rubin's galaxy catalogs could either bury this anomaly as a measurement artifact or elevate it to a crisis, revealing correlated redshift asymmetries that defy the cosmological principle. The same goes for quantized redshifts. If Rubin's vast dataset confirms those stair-stepped patterns, it would be like finding barcodes stamped across the cosmos, a signature of unknown order. But the real revolution might come from the unexpected. Rubin's relentless scanning will inevitably uncover objects that don't fit any template galaxies with impossible redshifts, supernova that burn too bright or too dim, or even entirely new classes of celestial phenomena. Recall that quasars, now cornerstone objects in cosmology, were initially dismissed as radio stars until their staggering redshifts revealed their true, extraordinary distances. Rubin could unveil similarly disruptive discoveries, forcing us to ask, have we been misinterpreting redshift all along? The stakes are cosmic. If these next-generation surveys confirm anomalies at scale, they won't just tweak our models, they'll demand a paradigm shift, much like quantum mechanics did for classical physics. Some theorists are already bracing for this possibility, exploring frameworks where redshift isn't a pure Doppler effect but a hybrid signal, blending expansion with quantum fluctuations, plasma interactions, or even multiverse echoes. Others warn of a cosmological crisis if the data contradicts lambda CDM so starkly that no patch, no tweak to dark energy or dark matter can salvage it. What makes this moment so electrifying isn't just the technology, it's the humility it demands. For centuries, science has progressed by assuming nature's laws are universal and unchanging. But if redshift anomalies multiply with better data, we might need to confront a universe far more nuanced, one where light stretching encodes not just distance, but the fingerprints of hidden dimensions, fluctuating constants, or realities beyond our own. The Vera Rubin Observatory isn't just a telescope, it's a time machine poised to show us not only where the universe is going, but how much we've yet to understand about where it's been. Science thrives not when it enshrines answers, but when it nurtures questions, especially the uncomfortable ones. The 28th clue in our cosmic detective story isn't hidden in telescope data or coded in starlight. It's etched in the history of discovery itself, the quiet rebellions that reshaped our understanding of the universe. From Galileo's heresy to Wegener's drifting continents, every scientific revolution began with anomalies dismissed as noise until someone dared to listen. Today, cosmology stands at a similar crossroads, where redshift's overlooked contradictions demand not just scrutiny, but a willingness to revisit ideas too quickly shelved as fringe. Consider Holton Arp's Atlas of Peculiar Galaxies, a catalogue of mismatched redshifts and cosmic oddities that challenged expansion's tidy narrative. For decades, his work was sidelined, his claims labeled artifacts of poor resolution. Yet modern telescopes like JWST now reveal galaxies with structures eerily reminiscent of ARP's ejected quasars, their filaments and alignments whispering that his ideas might have been premature, not wrong. The same pattern repeats with quantized redshifts. Once mocked as numerology, they've resurfaced in datasets from SDSS to DAISY, their statistical significance hardening with each survey. It's a cycle as old as science itself: dismissal, then rediscovery, often at great cost to progress. The resistance isn't just academic inertia. Science, for all its ideals, is a human endeavor, and paradigms wield gravitational pull. When a theory explains 99% of observations, the remaining 1% becomes noise by default. But history's clearest lesson is that the universe rarely obeys majority vote. Einstein's relativity bloomed from the tiny mismatch in Mercury's orbit Newton couldn't explain. Dark matter emerged from Zwicky's stubborn insistence that galaxy clusters moved too fast. In both cases, the anomalies weren't flaws in the data, they were flaws in the lens through which the data was viewed. Nowhere is this tension sharper than in the Hubble constant debate, where redshift anomalies might hold the key to reconciling conflicting expansion rates. Yet proposals to revisit intrinsic redshifts or plasma effects are often met not with curiosity, but with an almost tribal defensiveness. The irony is palpable. Cosmology, a field built on overturning dogma, now risks becoming captive to its own success. The Lambda-Cidium model's elegance has become its own trap, smoothing over contradictions with dark matter and dark energy patches rather than asking if the framework itself might need rethinking. This isn't a call to discard decades of work, it's a plea to embrace science's essential rhythm: doubt, test, revise. When Vera Rubin first presented evidence for dark matter, she faced outright hostility. Her response: more data. Today's redshift anomalies deserve the same rigor. The tools exist: Rubin Observatory's torrent of spectra, JWST piercing infrared gaze, even lab experiments simulating plasma redshifts. What's needed is the humility to admit that our cosmic map, for all its detail, might still have edges that don't quite meet. The most thrilling possibility isn't that we're wrong about redshift, it's that we've only grasped part of its story. Just as Newtonian physics wasn't overturned by Einstein but expanded, our understanding of cosmic expansion might be ripe for its next leap. The anomalies we've explored aren't cracks in cosmology's foundation, they're doorways. And behind them could lie not just answers, but questions we haven't yet learned to ask. So where does this leave us? 28 clues, each a whisper from the cosmos, each a crack in the foundation of what we thought we knew. From galaxies that refuse to follow the Hubble flow, to quasars that mock time dilation, to the eerie periodicities etched across the sky like cosmic barcodes, these aren't just glitches. They're pieces of a puzzle we're only beginning to assemble, and the picture emerging isn't the tidy, evenly expanding universe of textbooks. It's something far stranger, far richer, and far more alive with mystery. Science doesn't advance by polishing its triumphs. It moves forward by stumbling over its anomalies. Every revolution, from Copernicus to Einstein, began with someone daring to ask why the data didn't fit. Today, cosmology stands at that same precipice. The Hubble tension, dark flow, quantized redshifts, they're not nuisances to be explained away. They're invitations to dig deeper, to question whether we've been reading the universe's signals with the right key. Maybe redshift isn't just a measure of expansion. Maybe it's a chorus of voices, some singing of cosmic growth, others of quantum foam, plasma currents, or even echoes from beyond our horizon. Carl Sagan once wrote, "Somewhere, something incredible is waiting to be known." That's the spirit these clues demand. Not certainty, not dogma, but the humility to admit how much we still don't understand. The universe isn't a locked box, it's a living, breathing enigma, and every anomaly is a thread we can pull to unravel new truths. So here's the question I'll leave you with. Which of these clues fascinates you the most? Is it the binary stars defying gravity's rules, the redshift deserts where galaxies vanish, or the haunting possibility that our cosmos brushes against others? Drop your thoughts in the comments. Let's keep the conversation going. And if you're hungry for more deep dives into the unsolved mysteries of space, hit subscribe. Because the universe isn't done surprising us, and neither are we. The next breakthrough might be lurking in the data we've already gathered, or in the light of a star we've yet to discover. Until then, keep looking up and never stop.